Today we're going to talk about what happens when waves interact with each other. So if we have a wave coming from the right and a wave coming from the left and they run into each other, they're not going to bounce it off of each other like cars did in previous chapters, but they're going to have an interesting interaction. So first, let's look at this wave. So we have this wave here that's coming from the right, so it's coming along this way. This wave here that's coming from the left, that's coming along this way. So at this moment here, let's just draw and see what they look like. So as you can see, basically what happens here is the wave is just going to take the form of the red wave and the blue wave, and so they're just going to be on top of each other. So that's what it's going to look like at this point. Let's move down to a few seconds later after they get a little bit closer. At this point here, the waves have not touched each other yet. They're just right next to each other. So the total sum of the waves is going to be just these two waves right next to each other. So I'm drawing that right there. Now, when the waves actually overlap, that's when we start to see the weird things happening. So the spot where they don't overlap is going to be more or less the same. So we're going to draw that right now. But at the point where they overlap, they start to stack on top of each other. So right here, we see that there is this much of the blue plus this much of the red. So those two are going to actually stack on top. So right here, we start adding some blue and the red is all the way up here. They stack on top of each other. So we take this much blue and put it on top of the red. And so we're going to see a higher bump between the two waves. It's going to look something like this. So essentially, when waves run into each other, they add together what they have. So this is up here at this point, plus this red here. That puts us up here for the white overall wave. Now, when the waves overlap each other perfectly, this actually has a special name that's called complete constructive interference. So whenever two waves overlap each other and they're both going in the same direction, that's called constructive interference. And when the overlap is both of the waves entirely on top of each other, that's complete constructive interference. And that basically just looks like the same waveform, just twice as high. So the one before was a little bit wider because there was still those spots on the end where it trailed off. Here, they are exactly on top of each other, so it's going to be just twice as high. And as they leave and pass each other on the opposite sides, we see that same sort of growing and then the little top part where they overlap and then coming back down. And so this is what our wave is going to look like as they come together, run into each other, interact, and then pass each other. Now these waves are going to actually just pass right by one another without stopping again or without changing. And so once we get past this interaction, let's just pretend for a hot sec that there is another line below this that shows what they look like after they've passed each other. This blue wave is just going to continue on towards the left, looking the same way it came from the right, and the red wave is going to continue to the right, looking the same way that it did coming from the left. So they just pass each other, they interact while they're on top of each other, and then they continue on their way. Let's look at what happens when the red wave and the blue wave are opposite directions. So, of course, they approach each other, right? They get right next to each other, and so when they're at this point, it's going to be kind of a weird S-shaped looking thing. Now they start to overlap. So again, we're going to do the same thing we did before and trace on top of the red until the overlap starts. So if we see right here, kind of the overlap starts right at this point, so that's where we're leaving it. And then on the other side, we're going to do the same sort of thing, just trace over until the overlap starts. And once the overlap starts, we need to do the same sort of addition thing, but this time it's subtraction. So look, this red line right here is up here, but the blue below kind of drops off at that point and starts getting lower. So the red is going to have this here subtract the height of the blue and is going to end up being a little bit lower. So it's going to look something like this. Now we're going to keep moving down until at some point this wave is shorter, the red wave is shorter than the blue wave is negative. And so at that point we jump over and create something on the negative side. And we're going to come back up and meet our other line that we just created. So instead of being the gradual slope off that this pulse looks like, it's going to be more sharp because this blue wave kind of eats into it and pulls the slinky back down. Now, what about when they're right on top of each other? Before we called it complete constructive interference when they were the same shape and size right on top of each other. This here is going to be called complete destructive interference. So let's pretend for a second that I'm better at drawing and the red and blue waves are the same height. When they are on top of each other, they're going to completely cancel each other out. So this part up here that's positive is going to be added on to this part down here that's negative, and so it's going to cancel right through to the middle. So our line just looks like a straight line at this point. As they move past each other, we're going to get another weird looking S-shaped thing that kind of follows it, but then cuts off early, flips to the other side, and then follows it down. And then just like before, the two waves are just going to completely pass by one another, and our resulting wave is just going to be those two waves side by side. So when you are asked to figure out what the wave looks like at different periods in time, I would suggest you do something similarly to what I have done with the red and blue. Draw the individual waves and where they are at each period of time, and then over top of them, draw what the superposition looks like. So when we talk about a superposition, that just means two waves at the same position. So the superposition is like, okay, so this one is positive at this point here, the red or the blue was negative, and so it led to this drop off right here. So these are what these waves are going to look like as they pass past one another and interact with one another. So the next thing we want to look at is what happens to waves as they approach a barrier and then interact with that barrier. So let's say that this here on the right is just a big old wall that we have our piece of string or our slinky attached to, and then we have it pulled this way so there's some tension. So our wave approaches here and it gets close to the wall, and then at a certain point it'll hit the wall, and instead of traveling through the wall, which it can't do, or instead of running into it and stopping, what the wave is actually going to do is it's going to flip upside down. And so when it flips upside down, it's just going to travel back the other direction, but on the other side of the string. So if this wave now, let's say we created a negative wave and it went this way, it would run into the wall, and then once it flips to the other side, it'll just flip positive and come up here and travel back the other direction. So that's how waves interact with walls. They bounce off of them and go the other direction. So instead of going to the right, they'll end up coming to the left. But they also, the direction of the disturbance will change. Over here, it was positive, and now it'll become negative. Before we talked about constructive and destructive interference, but let's take a look at how that works in a physical environment with continuous sound instead of just one wave pulse. So let's take this example. Let's say I go to a concert, I'm sitting there, I'm rocking out, I'm really excited about this music, and there's two speakers on each side of the stage. So over here on the left, we have one speaker that is 2.5 wavelengths away from me for whatever sound is being played. So if we actually count, we have one wavelength from this peak to peak, another wavelength from this peak to peak, and then a half wavelength from this peak to this trough before it runs into me, the observer. Now, the other speaker has just two wavelengths before it runs into the observer. So peak 1 to 2 and then peak 2 to 3, that gives us two wavelengths before it hits me and I can hear the beautiful, beautiful sound of this music. So if we're looking at this in terms of constructive or destructive interference, the picture that we would draw would be something like this. So over here on the left, we have the wave at its negative point, and then on the right, we have the wave at its positive point. And so these two are traveling towards each other and will, when they hit each other, they will destructively interfere. Because one's positive and one's negative, and so they're going to cancel out. So really, in this spot that I'm seated, there's not going to be a whole lot of sound. It's going to be actually fairly quiet. There's an easier way to do it than drawing out these pictures and seeing where one is positive and one is negative. What you can do is you can just find the difference in the lengths between the speaker and the observer. So let's go ahead and label this x1 and x2. If we take x1 minus x2, this is going to give us some number of wavelengths. Now, if this number is a whole number, this means that the waves are going to be in sync with each other. So even if this was 3 on the left, we would be actually coming back up and would be at a positive just like we are on the right. So anytime you have a whole number difference in wavelengths, that means you're going to have constructive interference. But if you end up with a half wavelength number of wavelengths, this is the example that we have below, because this one had 2.5, this one had 2, so that leaves us with 0.5 is the difference in the wavelengths. And because of that, we have a negative for one of the waves and a positive for the other wave. So this would be destructive. So if we just find the difference in the two lengths and divide it by the wavelength, that'll give us the number of wavelengths. And if it's a whole number, it's constructive. If it is a half wavelength, it's destructive. If it's somewhere in between, then that means that it's not completely destructive, but there is some destructive wavelength. If it's closer to 1/2, there's going to be some destructive elements. If it's closer to a whole number, there's going to be some constructive elements. The last thing I want to talk about is kind of zoomed out a little bit. So before we were talking about the waves and when they run into walls and that sort of thing, and we talked about the disturbances. But let's zoom out a little bit and talk about light waves and light, instead of dealing with them as these waves that, wobble back and forth. If you think about what you typically see coming out of the sun, it's not waves like this. You typically see coming out of the sun just straight lines. And that's because while yes, they wobble, this center line is straight and it will continue forward forever. So essentially, when the sun creates a ray of sun or a bit of sun or a photon of sun, we'll talk about what photons are a little bit later. But basically, when it creates that, this bit of light just travels out from the sun in a straight line. Light rays are always going to travel in a straight line. Now, when this ray comes forward, let's say it keeps on going, right? So let's say there's a ray that comes out at this angle right now and just keeps on moving straight forward. And let's say this on the right is a mirror, and it runs into the mirror. What's going to happen to this sun ray? Let's take a look. Now, for simplicity's sake, we're going to just look at this mirror as a flat thing. I know I had that oval shape because not a lot of mirrors are oval shape, but the surface that the light is actually interacting with is going to be flat. So when we have a sun ray coming in, so let's say the sun produces a ray that moves, that's way too fat of a sun ray. Let's make this a little bit thinner. So let's say this ray moves like this direction, and it runs into the mirror at this point here. What is going to happen with the ray? Now, if you were to take a ball and you were to throw the ball at a wall and it bounces off, the angle is going to be the same as the incident angle. So this angle right here, if it was a ball, let's call this theta, that's going to be the same angle that the ball would bounce off of, also called theta. And that actually is the same way that sun rays work. So when we have a flat surface that it's reflecting off of, also known as a mirror, this angle that it ends up reflecting out off of is going to be the same angle as our incident angle. This is called the law of reflections. Now this actually gets quite a bit more complicated when we deal with something that isn't a straight line and we deal with a curved mirrored surface. So let's say that this orb over here on the right is steel ball bearing, stainless steel ball bearing. So it definitely has some major curvature to it. So if we have a incident light ray that comes over here from the right, comes up this direction, that is way too big for a light ray. Why are you so fat? Okay, so it comes over here from the right, and it hits at this point right here. Actually, let's make it hit at this point right here. What direction is this going to reflect at? There, you could say that the angle of reflection is just something super small like that. Or let's say you wanted to go all the way to the ball, it could be this big. Or if you wanted to go like here, it could be like that. But no, what we're actually going to be looking at is the normal. So if we take a straight line and just cut it through like that, that blue line right there is going to be the normal here. Let me make that a little bit bigger. So if we cut it through, that blue line right there is going to be the normal. And so that's the line that we're going to measure our reflection from. So our ray is going to travel this way right here, and the angle is going to be the same based on the normal. So if it's a flat, it's easy, we just do the angle. If it's a curved surface, we find the normal line and find the angle with respect to that. So that's how we do reflections. Hope everyone has a great Friday, a great weekend, and I will see you all on Monday when we're going to be talking about a little bit more about these reflections in mirrors.